Hello and welcome back to Calculus 1 Saturday edition. Today's lecture on Newton's method. Now, this is something that we really don't need today because of the era of computers and calculators and everything. Newton's method is used to compute a zero of a function, right? So here, use it to compute zero of the function. That's it. That's what we have. So compute zero of a function, and a zero of a function is where function cuts through x-axis. So that zero is also known as a root or x-intercept. And it looks like this. Right there. All right, we can call it c. So that f of c equals 0. This is your function, whatever the function is. So why we don't need any of this today? Because you can fire up Wolfram Alpha and just type in solve and type in equation and it spits the numbers out. So I don't care if you're sitting in engineering or you're in business or whatever you are, right? You can always fire up Wolfram Alpha and the Wolfram Alpha is going to tell you, oh, okay, here you go, 1, 2, 3, right, done. It doesn't have to be Wolfram Alpha. There are, many other websites where you can do this. So we are technically learning this to to honor our ancestors, but it's a cool thing because yes, we get to use the derivative and blah blah blah, but it's also cool to see what people used to do before. And another thing is this is opportunity for those of you who are computer science majors to go and program it, which is way more important than doing any single homework problem or answering question correctly on the exam. Many of you will have to program to pass your, 300-400 level courses when you transfer out to four-year school. And many of you will have to program so you can, and I'm not talking about computer science majors, I'm talking about, electrical, mechanical, and so on. Many of you will have to program and understand how to work with computers in your field. A lot of simulations and things are done on a computer, right? Before you make a prototype. So I hope that you guys will be programming this, whether it's Java or a Python. I'm gonna, push for Python a little bit more, obviously, because, right, welcome to 2020. But yeah, this is something that you guys could do, right? And it's a very simple loop for you to program this in, and I hope you will. I don't care if you're a computer science major or not, you should be able to program these very simple ideas. Now, as I said, this is going to compute the this intercept. And the way we do this is we use the tangent lines, but since this point will be in quotation marks moving, right? There is a formula that can always compute the next value, and so on. So let me write down the Newton's method. We're not going to derive it because, again, this is not an honors course. I did tell you it's coming from the tangent line calculations, but I'll show the picture at least for that. So the Newton's method says that so given x0, and I'll just put start point. For n equals 0, 1, 2, blah, 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 blah. we can compute Newton's method as xn plus 1 is equal to xn minus f of xn over f prime of xn. And this is the formula that you would program into your for loop and go for it. Oh, we could just also say that f prime of xn is not allowed to be 0. I mean, that should be common sense because it's in the denominator. There we go. Now, why does this work? I'm going to draw a picture here with some function that has a c over here, and let's pick our x0 right there. Now look at this. When I go up and find this value, and then I put the tangent line there, you see that the tangent line cuts through x-axis. Try to, there we go. See, the tangent line cuts through x-axis and creates the new value, which I'm going to call x1. Now you see that x1 is closer to the root than x0. Then, from that point, you're going to go up. Let's go blue. And draw another tangent line. Now that creates x2. And you see that x2 is closer to c than x0 and x1. Then you can go, let's say, purple. We go up to that point. Draw another tangent line that gives us x3, that it's almost the same. This is obviously approximation. It's not going to give you exact root. But the amount of calculations that you do will give you better and better and better result. Eventually the decimals are going to start lining up and so on. So maybe after 1,000 calculations you can have 12 well, not 1,000 calculations, you can have 12 decimals match up and so on. So the goal is to just run this formula. Now this index writing here is just going to be this 0, 1, 2 that are in the index of your number, telling you what x value you are using. So this formula here, where we say n equals 0, you are getting x of 0 plus 1 is equal to x0 minus f of x0 divided by f prime of x0. Well, x0 plus 1 is just x1, right? So you see that you are able to find this better point, x1, by using all of the calculation with all of these x0s, which is really, really cool concept. Now, Newton did figure this out. Now, obviously, he had to figure it out because when he did this in 1600s, there were no computers, and polynomials are the nastiest functions out there to find zeros, right? Yeah, it's easy if you have x squared of some kind, like quadratic, right? Use a quadratic formula, you're done. But if you're interested, go and look up the formulas for a cubic polynomial. Then there is a procedure for the quadric polynomial, right? The x to the fourth, which would take you an hour just to get the first root out of 4. And then there is a proof that procedures and formulas cannot be even written for 5th degree and above. So welcome to polynomials, right? Everything else is easy. Like trig is easy. You take inverse trig, and e and ln opposites of each other, and this, exponential and square roots as well. Like this is a lot of stuff that you guys can do to find roots for all of those. But for polynomials, living nightmare. right? And this is why, right, we get to do the this method. Newton invented this method so he can, you know, just to figure out what is like the x cubed minus 5x plus 6. Like you can't factor it, you can't group it, you can't do anything with it, right? It's absolutely living nightmare, right, to solve this problem. So this method, right, would work. And then, you know, for n equals to 1, you have x2 is equal to x1 minus f of x1 over f prime of x1, but you already have x1 because you computed x1 in the first route. So this over here will give you x1 equals to some number, and then you will feed that into the equation again, which is why the basic loop um, solves this problem. You should have just, you know, with input and output and all of that, no more than the 10 lines of code. All right, to come up with something like this. It's a good exercise. Now, um, as you can see, you need to be able to take the derivative. Now, obviously, function and the derivative, you can hard code into your code, or you can you know, put an input so that it can be typed in, but you know that will require some advanced knowledge. I'm perfectly happy with, you know, if you code this with just basics, you know, and hard code literally everything else in it, then yeah. But you can also leave it an option for people to plug in their own function and their own derivative. You can even actually take the derivative in some sense through code. And then you can also say how many times you want to run this calculation, right? Because this is me running it once, then running it a second time, running it a third time, and so on. But you can also detect the difference in the answer. So you say, okay, my precision now is 3 decimals and so on. So I have a lot of these different variations. If someone wants a little bit of a programming challenge, let me know. And I will guide you the way I'm guiding the math club to, you know, work on their AI and all of the stuff. I will guide you the same way to develop the software from, you know, having the basic 10 lines into having some features that we can actually use in the workforce.
So, Professor, if I
Yes,
program this, when I emailed it to you, you would see it?
definitely, yes. I actually have a
Okay.
student who already emailed me the code from the other class.
Oh, okay.
Look, as
Okay.
I said, I'm going to look into everything. So if you email me the code, well, we will be talking about a code. If you ask me what your what your grade is and when are the office hours, I'm just going to delete the email. So
I get you.
there is a difference, right? As I said, I'm not deleting emails because I'm bad. I'm deleting emails because you're bad. You have to look up information that is already available, right? And
Yeah.
not bother me with it. But yes, if you email me the code for Newton's method, I am going to 100% work with you, and I'm going to suggest, you know, the next step. You do again. This is not something you're graded on. This is
Yeah.
a life skill that will make it better for you down the line, right?
Okay.
So having and having fun with, especially if you're computer science, right,
Yeah.
where most of the students sitting in calculus 1, they don't get much for the computer science,
Yeah.
because your goal is to get to calc 2, so learn sequences of series, which is computer science. But you know, in calc 1, like, programming this is a huge win for you. All right, now let's take a look how to do these problems by hand, which obviously, you know, takes a lot of time and effort. And then we can go and figure out the rest. So what should we can either do sine x. I don't remember which problem I worked with the other section, because you can watch their stream and take a look at that problem. And or well, sine x plus x, I guess, problem 15. So f of x is equal to sine x plus x minus 1, and they want us to start at 1/2, which is 0.5. So this is problem 15 from the homework. And this is literally the only exercise we're going to do because this changes, which changes the derivative. We have to take problem to problem. There are no variations or anything like that. So we start by figuring out the derivative, which is cosine x plus 1. And we just need to start cranking the formula, where n is equal to, and I can write the formula here, right, which is your xn plus 1 is xn minus function of xn divided by the derivative of xn. So when n is equal to 0, we already said that's going to be x1 is equal to x0 minus f of x0 divided by f prime of x0. Now, for our numbers, x0 is 0.5, right? And then you have minus. Now, the original function is going to be sine of 0.5 plus 0.5 minus 1. And then cosine of 0.5 plus 1. Okay, so now you have to make sure that your calculators are in radians. You go to the mode, right? Because 1 radian and 1 degree is not the same thing. Just a quick reminder from your pre-calculus 2, right, the trig course. This is when you put those pi over 2 and pi, those are the radian measurement. Now, pi radians is approximately 3.14 radians, which means that if I am to put the numbers around this circle, I would put about 3.14 there, which would make, let's say, this number 3. Now I have to cut this one into 2, so maybe, let's say, over here somewhere is going to be number 1, and over here somewhere is number 2. Whatever they are, right? So a measurement of 1 radian would be this measurement. That's 1 radian. And then half a radian would be somewhere here, 0.5 radian, because that's half of the angle. Now, your 1 degree is a full circle divided by 360 divisions. So 1 degree is this, you can't even see it here, 1 degree, which means that a half a degree would be half of this. You know when you go to a party where some kid has a birthday and then you find that those slices of pizza that are like you have to eat like 100 just to make up for one slice? Well, technically 1 degree is even worse than that. All right? So you are taking the entire circle and you cut the entire circle in 360 pieces. Each one of those slices are going to be a tiny slice, where when you cut the entire pizza here into 6.28 pieces, call it 6, okay? So you see how much difference is between 0.5 radians and 0.5 degrees. Visually, just by looking at this difference here, right, you understand that when your calculator is in a wrong mode, your numbers are going to be off by a lot. So your job is to make sure that when you are in a math class, you keep your calculator in radians so you can graph the trig functions and see them. If you ever graph trig functions and nothing shows up on a graph, it's because your calculator is in degrees and the graph is not visible where you're looking for it. So what you need to do, guys, is just to get your calculators in radians by pressing the mode button. And once the calculator is in radians, then you can go and plug all of these values in. I'm just going to get all of this trig off, and again, if you need to refresh any of this stuff that I said, you can just watch the video on YouTube again. There we go. All right, so now I will be calculating x1, 0.5 minus, open parenthesis, sine of 0.5, closed parenthesis, plus 0.5, well, plus 0.5 minus 1, that's just minus 0.5. Then we're going to close the parenthesis on top, and then we're going to divide it by another parenthesis on the bottom. Is cosine of 0.5 plus 1. And I am getting 0.51096. Now, one thing about significant digits and all of these kind of things, guys, especially those of you who never had chemistry and physics, dragging this many decimals on the input that it's this, right? It's like, yeah, I don't really need to, because look, if your measuring device allows you to have a 2 decimal precision, then you cannot make better measurements than 2 decimal precision, which means that if you need to cut something for mechanical engineering, you can't cut it better than the 2 decimal precision. I'm just giving whatever example. Maybe you can do it 4 decimals, maybe you can do it 10, I don't care. But the trick is that when you made your measurement, you can count, you can cut to a specific precision because of the tools and so on, right? So now, when you have 0.5 as your input, that tells me that I can only measure 1 decimal. Does it make sense to provide 5 decimals in the in the calculation for x1? No, it doesn't. It doesn't, right? Because if I go and say, oh, okay, for whatever thing that I'm doing, you know, the value is, and then I give 5 decimals and I can only cut and measure 1, right? So your cutoff points are always 1 decimal extra, with everything beyond that being completely pointless. Now, I am going to keep 3 decimals because the error is going to accumulate throughout. Actually, maybe if I keep this as 9.6 and then just say 0.511. And now I'm using this one again in the formula when n is equal to 1 to calculate x2, which should be the better answer, which is going to be x1 minus f of x1 divided by f prime of x1. That is going to be 0.511 minus sine of 0.511 plus 0.5 minus 0.511 divided by cosine of 0.511 plus 1. And we go from there. The same calculation, and you go and compute. Now, those of you that are interested in use of a calculator, you can use VARs button to calculate these functions instantaneously. You can set up f and f prime in VARs in the calculator, and then you can call on that. So, and the way you do it is actually you push y equals, and you put your your original function f in there. So you just say sine x plus x, close parenthesis, plus x minus 1. And then you go to y2 and you set up your derivative, which is cosine x, close parenthesis, plus 1. So you set up these two functions in your regular graphing window, right? Regular graphing window, where you have that y equals. So when you set those functions there, what you do is you go second quit, right? And now instead of typing all of this one by one, you will only type 0.511 minus, and then you're going to push vars button, change it to y vars, which is you go left, and function is already highlighted. So you pick y1, you open parenthesis, and you write 0.511, close parenthesis, divide, you push vars button again, go to y vars, push equal to function, and pick y2 now, and open parenthesis 0.511. So if you're using vars, so set up y equal, so y1 is the function and y2 is f prime. So now my x2 looks like this, 0.5511 minus y1 of 0.511 divided by y2 of, so this is what your screen should read. And when you push enter, it gives you x2 of 0.51097. Oh, maybe I would have kept more decimals on this one. So now, when you have this, right, you keep going. Now I see that I actually chopped off the decimals, because look at this decimal, look at this decimal, right? So it seems that it's hovering actually on 511 as the answer. But the idea is to keep computing this over and over and over and over again. Obviously, if you're writing a software code, let it do 100 times, right? And when it spits the answer, that should be a zero of your problem, right? Where the function cuts through the x-axis. Now there are some rare cases where this method fails, and I don't cover them in class just because, you know, as I said, this is a section where we learn to honor our ancestors, and this section is mostly useful to all of the students who want to practice programming. Obviously, for the exam, you can use the software, you can use the calculator, you can use, right? So it's kind of even pointless to put this on a test. At Rutgers and NGIT, you have to do these calculations by hand because they have a zero calculator policy there, meaning you can't even bring the solar calculator with addition and subtraction on it to the test. So you would actually have to compute all of this by hand, which is, yeah, good luck, right? But the idea of the entire section is, yeah, you have this one formula and you just keep recomputing the same formula with the new number that you get. And as we see in the picture, right, every number that you get, x1, x2, right, they're always closer and closer to C. And now you can actually already see here that, right, this one is already 0.511, right, again. So I can just say that the solution is about 0.511, right? It's just because they're already all lining up there. And since these two numbers had the first four decimals, right, be the same, right? Maybe the next one is going to go at 8, or maybe it's going to stay at 7, and then we're going to get the next decimal, right, change or something like that. So you will see it, right, where it checks, and then you go from there. All right. Well, believe it or not, that's it for Newton's method. I mean, it's nothing else here. It's just arithmetic, right, to compute everything. I mean, yeah, you have to find the derivative, so you can be calculating in the derivative as well. But that's all it takes, right? You have a function, you find the derivative, and then just keep calculating the formula. That's all it is. Keep calculating the formula, and once your values, the numbers, right, line up, then you have your solution. And again, this is approximation. You are not getting exact answer, but it's very useful. And especially where this is useful is for this type of problem that cannot be solved algebraically, right? So that's one last thing that I'm going to say. So if you have a problem like 2e to the x minus 1 is equal to x plus 3, right? This problem cannot be solved by any means of algebra, pre-calculus, whatever, right? Because you have a transcendental function mixed in with a linear function. And they are in different areas of existence, right? Because, yeah, you can add 1 to both sides, right? Get your 2e to the x equals to x plus 4. Now what? When someone will say, divide by 2. Okay, sure. Divide by 2. You get your e to the x is equal to x over 2 plus 2. Now what? Well, it's simple. ln both sides. Okay, ln both sides. If I ln both sides, what do I get? I get x equals ln of x over 2 plus 2. So I freed up this x, but I buried this one. Oh, okay, well, we can take this one if I e both sides. Yeah, but then you're back here. Just there's no way to solve this. There's no way to solve this using what we call analytical methods, right? Calculation with algebra, pre-calculus, and so on. For this, you have two options. What we did now, program it in, because what you are going to do here is you're going to turn this into a problem that you can work with, because you are going to say 2e to the x minus 4 equals 0, right? So you put everything on the same side. Now you make that into a function, and then you can look for a 0 of a function. And now, boom, computer, Newton's method, right? And you're done. Or graph, right? That's the other way. So you have your 2e to the x minus 1. So you will graph two functions. So minus 1 is going to go like this something, right? So that's your exponential function. And then x plus 3, 1, 2, 3, let's say, it's going to look like this. So they intersect here, and whatever that x is, right, is your solution. And they also intersect here, so there's going to be a negative x as a solution. So these types of problems where you're mixing trig with polynomials or exponential with polynomials, well, exponential mixing with trig you can actually solve, because there is a connection between sine x is equal to e to the ix minus e to the minus ix over 2I. So there is a connection through complex numbers. There is a connection between the trig functions and the exponential functions. So we know that. So you could solve e and sine, right? Or ln, right? If they all show up in the same equation. But if you have a polynomial mixed in with any one of those, your only two options are numerical calculations with Newton method or graphing. And that's it. That's the end of your options. So it is very important, but again, we don't actually need to know this, because the computers and everything is programmed, unless there is an apocalypse, right? as that meme would say, what if, what if 2020 was just a sneak preview trailer for for 2021, right? Meaning that, yeah, we're just getting warmed up for much worse coming up next year. But anyway, that's it for Newton's method. We're going to take a break, and then when we come back, um, we are talking about integration. So last section of chapter 4, 4.9, on what we call antiderivatives, which are technically integrals. So I'll see you there soon.